Hello, Math 8 students. This is Open Up Resources Unit 1, Lesson 16, Parallel Lines and Angles in a Triangle. This is the last lesson of the entire unit, so that's why a lot of the stuff is very familiar. It's because we're really trying to just bring everything all together. This is the second in 2 videos that are covering this lesson. And I'm not going to spend a lot of time reviewing what we did in the last video. I just want to be able to dive right in. So we're moving on to 16.3. This is activity 3, every triangle in the world. And we start by looking at this diagram. And it tells us that we have triangle ABC here. And it says line DE is parallel to AC. So we've got that base of the triangle, forms the base, but if we extend that, it forms this line AC. And it is parallel to DBE. And we start by asking, what is the measure of angle DBE plus B plus the measure of angle CBE? Let's take a look at that diagram and let's color code it as we go through that slower. So it says, what is the measure of angle DBA? So D to B to A. I underlined it blue here, so I'm going to go ahead and mark that angle blue here as well. Plus B, well, that would be this angle right here. Here is angle B. I'm going to go ahead and color that one red. And measure of angle CBE, CBE, you can see that we've traced out this angle here. And again, I'm going to color code that one in green. Now that I've actually color coded it, now it's easy to see what we're actually talking about. When I take blue and add it to red and add it to green, what do I get? Hopefully you've seen this enough times that you know that this is a straight angle. And a straight angle, that means that it adds to 180 degrees. They are supplementary. So straight angle adds to 180. Let's write that down. We have blue angle plus red plus green. And what does that all add up to be? That all adds up to be 180 degrees. How do I know? Because it's a straight angle. Now, it says use your answer to explain why A plus B plus C is equal to 180 degrees. But now I'm looking at A plus B plus C. So we already know this. We've proved it before. We're going to be looking at it a little bit differently this time. You'll notice that what I've done with this diagram is I've now adjusted it. Remember, it was a triangle, right? And we had our parallel lines. But what I'm doing now is I'm going to focus on this line. I've extended it so it looks more like a transversal, where it cuts all the way through and it continues on. But I'm also, just so that we're not distracted by it, I'm going to cover up this piece of the triangle, trying to white it out there a little bit so that we're not focused on that. I don't want us to see the triangle. I just want us to see a pair of parallel lines and the transversal that goes through them. And we're going to use that to answer this next question. Can we explain why that A plus B plus C is also equal to 180 degrees? So look at the parallel lines and look at the transversal. Here we have this blue angle, right? And I want you to remember alternate interior angles. That means inside of the parallel lines, where this one is, but on the alternate side of the transversal and looking at the alternate line in the parallel pair, we can see another angle that is the same. So here is blue angle, but the alternate side is going to be down here. Remember, that's alternate interior angles are congruent. And so I was able to color in angle A as blue, knowing that it's the same measure as that angle up above because of that alternate interior angles. I'm going to write that down. Angle A is the same as angle DBA because alternate interior angles are congruent. And now, with that in mind, I want to take a look at the diagram again, but in a little bit different way. So take a look at this diagram. Again, take a look at how I've modified the diagram. We already know that this is angle blue, right? So now I'm going to focus on getting rid of that piece of the triangle so that I'm not focused on the triangle. And now I'm extending this line of the triangle, bringing it back into focus. It was whited out before. It's back into focus. And now again, I've extended that line so that it now looks like a transversal that's cutting through that, because it is. It was just cut a little bit short, but now I've extended it. And so again, we can see alternate interior angles, this time focused on the green angle. Because again, this green angle is on the inside of the parallel, and here is the alternate angle. It's on the opposite or alternate side of the transversal, and it's on the alternate pair of the parallel line. So we're switching sides of the transversal, switching from the top line to that bottom line, and so we can see that this angle C is also going to be colored in. It's going to be colored in green because it's the same as this one up here. So again, let's write that down. Angle C is the same as angle CBE because alternate interior angles are congruent. And so with that, we can now officially answer that question too. And we can see, now I've gotten rid of both of those transversals, and now I can again just focus just on that triangle. But using those properties, I can see that this blue angle is the same as this blue angle. And this green angle is the same as this angle here. They're both colored that green color. And so here we have blue plus red plus green is 180 degrees because it was a straight angle. But blue, which is now this angle, plus red, still the same angle, and green, which is this angle, is also going to be that 180 degrees. So I'm kind of out of space here to answer that question there. So I'm going to go ahead and kind of answer it here, where it also says, explain why your argument will work for any triangle. That is, explain why the sum of any angles of any triangle will measure to 180 degrees. So I'm taking that same information and I'm applying it down here, right? We're always going to have those alternate angles being congruent. And so that means that I will always have that blue angle in the straight angle will be congruent to an angle in the triangle through alternate interior angles. And again, we'll always have a green angle in that straight angle. And it will always be congruent to an angle in the triangle. Through that alternate interior angles. And so, just like we saw up here, blue plus red plus green is equal to 180 degrees because it's a straight angle. That means that I'm going to have that blue plus red, oh, hold on. I'm going to have that blue plus red plus green. Even if it's a different place that that blue plus green plus red is going to be, it is still going to equal that 180 degrees. This time it's not a straight angle, it's just been rearranged to a triangle. And again, we're not surprised by this, right? We've seen this before, we're just proving it a different way. And are you ready for more? I want to do this one a little bit quickly because we are going to be doing a calculator exploration about this. So it says, using a ruler, create a few quadrilaterals. I am just going to create two very small ones. You can create some different ones, but I want you to observe what we're doing here. My first one is going to be boring, and it is a rectangle. And we know that rectangles, by definition, will have all of these angles measuring 90 degrees. Okay, so what is the sum of all of those angles? Well, 90 plus 90 plus 90 plus 90 is equal to 360 degrees. Well, what if I created a little bit different quadrilateral, and for lack of having a bunch of space, I'm going to come down here and do it with number 2. What if I created this really weird shaped one? Or what if I created this also super weird shaped one? What are those going to add up to be? So I'm going to pause the video so that I can use my protractor and actually measure those, and then I will return to the video once I have measurements, and then we'll talk. In the meantime, you should also pause the video, and you should draw some quadrilaterals and measure those angles. Then we'll talk about it once you also have measures to your angles. Pause the video now. Okay, I got all of my angles measured. I hope you do too. Since we're looking for the sum of all of them, 57 plus 74 plus 78 plus 151, all of that does, I already checked it in my calculator, it does add to 360. Here, 130 plus 140 plus 48 plus 42, I also checked that one, and it also sums to 360 degrees. So, why is this happening? Why is it that they always add up to 360 degrees? Part 2 says, hint, draw a diagonal in in each of the quadrilaterals, just one diagonal. So what does that look like? We first need to understand what a diagonal is, and a diagonal connects non-adjacent vertices. So if I start at this vertex and I go to this vertex, those are adjacent, they're next to each other. That just forms a side. If I go from this vertex to this vertex, again, those just form sides because they are adjacent. I need to go to a non-adjacent, and there we have a diagonal. Same thing here. I'm going to go non-adjacent to create the diagonal, vertex to vertex, and you can see that there. And I'm just drawing random ones. I could do it the other way. I could draw this one. I could switch it and go this way instead. Either way, it's the same. We're just drawing diagonals. And when I draw that diagonal, I want you to pay attention to what happens with that shape. Why is it that they're always summing to 360 degrees? Notice that when I use that diagonal, it's cutting the quadrilateral into two shapes. It's cutting it into this triangle here and this triangle here. Same thing. This triangle, two triangles. Here, this triangle and this triangle. So why is it that they're always adding to 360 degrees? Because we're always seeing 1 and 2 triangles. And if triangles add to 180 degrees, then 2 triangles are going to add to 360 degrees. So why is it happening? It's because quadrilaterals are formed with a couple of different triangles. Remember that because that's going to come up in our calculator exploration. All right, time for the next and final activity. This diagram shows a square BDFH that has been created by taking triangle ABC and doing rigid transformations to it. So first focus on that ABC. How does it change to be CDA? How does it change to be EFG and GHA? And hopefully it's pretty easy for you to see that they are changing by rotations. We're rotating 90 degrees. And so I also want to focus on this. This is a right angle. So of course, when it's rotated, then angle D is also going to be a right angle. Angle F is also going to be a right angle, and angle H is. Now those are marked for us, but it makes sense because it's just a rigid transformation. I'm rotating this triangle to be this one. And so of course it's keeping that angle measure. So I don't know what this angle is. I'm not using a protractor. I don't even want to find it out. I just want to know if this is blue, whatever blue is, if it's blue, what other angles are also going to be blue? Think about those rigid transformations. BAC is going to rotate to DCE, so this is also going to be angle blue. And that's going to rotate again, and this is going to be angle blue. And rotating again, and this is going to be angle blue. Okay, well what about this one? What if I made this one angle green? Then angle green rotated is going to be down here, also going to be green, because the angle measures don't change when we are rotating that triangle. Rotating and rotating. So, what is it that you're noticing here? Can you figure out any of these angles? Before we even look down here, I know it tells us that that's 53 degrees. I don't even want to worry about that. Again, I want us to focus on the fact that we have blue plus red, right angle, plus green. We know that that adds up to 180 degrees. We also know that this line right here is a straight angle, so that's also going to add to 180 degrees. So think about this. If blue plus red plus green is 180 degrees and green plus something plus blue is 180 degrees, I think it makes sense that this red would also have to go here, and so this is a right angle. Knowing that that's a right angle, again, we can follow that same strategy and see blue plus something plus green is 180. If we know blue plus this red, right angle plus green is 180. So we can follow on and see that each one of these angles is indeed a right angle, just as it appears to be. And from there, we can go through and say, oh, okay, BAC, so that's our blue angle, that has a measure of 53 degrees. This is 53 degrees. So each one of these is 53 degrees. We already know that red angle is 90 degrees because of that marking that it was given to us. So let's use that information. Let's also see if we can figure out green angle. I'm trying to write all of these in here. Use your calculator and figure out what is the measure of angle green. There's lots of ways you can do it. Depends on if you're looking at the straight angle, depends on if you're looking at the triangle, but the whole angle would have to sum to 180 degrees. So green plus our 53 degree blue angle plus our 90 degree right angle all has to add up to 180 degrees. That means that green angle, I told you to enter it in your calculator. Hopefully that bought you enough time and you have entered it. 37 degrees. Green angle is 37 degrees. So each one of these angles here is 37 degrees. All right. Cooldown is what's next in your packet if you printed that packet. Let's go on to the summary first. Using parallel lines and rotations, we can understand why the angles in a triangle always add to 180 degrees. We can see this diagram, triangle ABC. Line DE is parallel to AC and it contains B. Notice that we've changed that diagram even more. All of our diagrams in our examples today at least had these parallel lines. We've shortened that second parallel line to just being the line segment of that triangle. But AC is parallel to the line DE, and we can see B right here is on that line. 180 degree rotation of triangle ABC around the midpoint of AB. That's what we did in our last lesson from lesson 14. Rotating that around, we can see that X and X are congruent. Rotating it around that midpoint, though, is how we came up with alternate interior angles are congruent. So although we can rotate, I also want us to not lose focus of that alternate interior angles. That's an important one, so I'm going to write that down. And if we continue on, it continues to say that we could also take this triangle ABC and rotate it 180 degrees around the midpoint of BC. And again, that's going to take angle Z to this angle Z. Again, we also know that through that alternate interior angles being congruent. Rotating it is what helps us form that theory of alternate interior angles are congruent. And so we can see that since those angles, once they're rotated, they form that straight angle here. That also tells us that those same angles, even if they're in different positions, are also going to add up to 180 degrees. So that straight angle, which is 180 degrees, even if I take X and I move it down here and Z and I move it down here, they will still add up to 180 degrees. So the sum of the angles in any triangle will always be 180 degrees. Now let's head back to our cool down. In an equilateral triangle, the side lengths are all equal and all angle measures are equal. So sketch an equilateral triangle and what are the measures of the angles. So again, this is just a sketch. It's not going to be perfect. Trying to make all of my sides the same and all of my angles, and it's not perfect. I hope that it's close enough for you. Key thing is that whatever this is the same because it's an equilateral triangle, and this is also the same. So x plus x plus x has to be equal to 180 degrees. In other words, x plus x, well, that's 3x, is 180 degrees. So what must those angles be? 180 divided by 3 is equal to 60. So each one of these angles would have to be equal to 60 degrees. What about an isosceles triangle, which is not equilateral? That means two side lengths are going to be the same, and two angles are going to be the same. Sketch 3 different isosceles triangles. Here's one. Again, these are not perfect. They are sketches. Even with my line tool, they're still sketches. This one's harder for me. All right, there's my 3 different isosceles triangles. What could these angles possibly be? This one is obtuse. So these ones would have to be the same. And I don't know what this angle is, but I know that it's obtuse, so I know that it's going to be bigger than 90. Let's maybe say it's 130 degrees. So again, think about this. 130 plus x, it still is going to equal 180 degrees. X plus x, well, that just means 2x. So remember, I've already got 130 degrees taken up here. So that means I have 2x, which is equal to 50. Let's go ahead and divide each side by 2, and we can see that x would have to be equal to 25. So we could have a 25 degree, and 130 degree. That would take care of this one here. What about this one? This one's definitely acute, definitely not as big as that one. And again, I'm not sure. Let's say it's roughly, let's say it's about 50 degrees. Remember, isosceles means that this angle, I'll use a different one, I'll use y. This angle would have to be the same as this. Whatever it is, they would have to be the same. So again, that's going to be 50 plus y is equal to 180 degrees. But again, these are the same, so 50 plus 2y is 180 degrees. 50 degrees of that 180 is already taken up, so I'm going to go ahead and subtract that. And that tells me that the 2y would have to be equal to 130 degrees. Let's divide each side by 2, and I know that y, whatever that angle is, would be 65 degrees. So another option for this triangle here would be about 65, 65, and 50. Obviously, there are lots and lots of other ones. You can see here, I've got yet another one. I'm not going to answer that one because it just says list 2 different possibilities. But you can see that no matter what the special circumstances are, there's always the most special circumstance that it's going to add up to 180 degrees. So that's it for today. You have your lesson 16 practice problems. Please don't forget to answer your cool down in Canvas and work on those lesson 16 practice problems. That's it for today. We'll see you next time.